Hi, I am Lina. I'm Network Solution Engineer. Modern networks require speed, consistency, and reliability. As infrastructure grows, manual configuration becomes difficult to maintain and often leads to errors or inconsistency. Teams need a way to deploy services predictably and keep the network aligned with the design. In this context, two concepts become essential: infrastructure as a code and the single source of truth. Infrastructure as a code allows us to treat a network configuration like a software versioned, reusable, and automated. The single source of truth ensures that every decision and every deployment is based on accurate, validated data. In this demonstration, we will show how Nautobot, acting as a single source of truth, and AWX, acting as automation engine, work together to deliver an end-to-end automated SPB deployment. By combining both systems, changes flow directly from intent to implementation without manual intervention. Everything you will see today is done in a lab environment, but the same workflow applies in the real networks. Let's begin.
Let's take a look at today's agenda. First, we will quickly review the core automation principles, infrastructure as a code, and the single source of truth, and show how they work together. Then, I will introduce the two tools we used, Nautobot and AWX. After that, we will look at the lab steps, and finally, I will walk you through the live demo. And we will finish with the key takeaways. Before we start the demonstration, I would like to quickly introduce the three key concepts behind it: infrastructure as a code, the single source of truth, and how these two work together. Infrastructure as a code means that we manage the network the same way developers manage software. Instead of logging into devices and configuring everything manually, we describe the desired configuration in code. This means three things. We write the configuration in files like YAML, JSON, or Ansible playbooks. We store them in Git, so everything is versioned, and we apply them automatically with automation tools. In our demo, this will be done through Nautobot and AWX. A single source of truth is simply one central place where all the correct and validate information about the network is stored. That includes device, interfaces, the SPB topology, services, SAP, and more. In our case, Nautobot is our single source of truth. Now, why is this important? One place means no contradictions, avoiding manual mistakes, and it keeps the documentation aligned with the real network. How do these concepts relate? The idea is simple. The single source of truth describes what the network should be. Infrastructure as a code applies this desired state on the real devices. So Nautobot provides the structured data, and AWX uses this data to generate and push the configuration. So Nautobot defines the intent and AWX enforces it. We integrate both because this is what gives us an end-to-end automated workflow. We first onboard the real infrastructure into Nautobot manually to make sure the model is accurate. Then all changes are driven by code through AWX. AWX executes the automation reliable and repeatedly, and with webhooks, the whole process becomes event-driven and automatic. In the end, this provides faster deployment, fewer errors, and perfect consistency between documentation and actual configuration. That the concepts are clear, let's move into the actual demonstration. The first things we did was establish connection between AWX and Nautobot. This integration allows AWX to automatically retrieve all the infrastructure data stored in Nautobot and to keep its inventory continuously updated. Normally, without a source of truth, you would have to update your AWX inventory manually every time the network changes, sometimes several times in a year. Here, Nautobot acts as the live, authoritative database. AWX always pulls fresh, accurate data directly from it. The result is simple: no outdated inventory, no manual maintenance, and no risk of configuration drift. Now let's see how the automation actually works. In this demonstration, we will automate SPB configuration across the infrastructure. To keep it simple, let's imagine a real use case. An administrator wants to create a new SPB service on a switch 1. Because Nautobot is the single source of truth, the change must be done there and not through another tool. Once the administrator creates the SPB services in Nautobot, several things happen automatically. Nautobot triggers a webhook. The webhook sends a REST API request to AWX with a JSON payload that includes all required configuration details. So AWX receives the request, identifies which job template to execute, and pulls the corresponding roles and playbook from Git repository. And here, GitHub is where we store all the automation code. So AWX connects to this repo, and before each job, it's synchronized to make sure they run the newest version of the playbooks. And we use GitHub because it keeps all the code centralized, tracks every change. So in one sentence, GitHub holds the code, Nautobot holds the data, and AWX applies the configuration. And AWX then runs the Ansible job. The configuration is dynamically generated based on the data coming from Nautobot. Finally, AWX pushes the configuration directly to the target devices using the appropriate network modules. Before deploying to production, we can also validate everything in a digital twin environment. In our case, we use GNS3. This allows us to simulate the network behavior, check the generated configuration, and ensure the automation behaves exactly as expected before applying it to our real switches. Let's look at Nautobot and AWX in more detail. What is Nautobot? It's an open source, acting as source of truth and automation platform for networks. It centralizes all infrastructure's data and exposes powerful API like REST, webhooks, Git, etc. to drive automation, flexible and extensible. It lets you model your network, enforce data accuracy, and build custom automation apps on top of it. And now, where is AWX? It's the open source web platform for running and managing Ansible Tower automation. It provides a visual interface, role-based access control, job scheduling, login, and integration, making it easier to control, scale, and delegate Ansible playbook execution across your infrastructure. In this demonstration, we will deploy an SPB shortest path bridging architecture on a lab, composed of 4 interconnected switches. We assume that each switch operates as a BEB, backbone edge bridge, meaning they handle both backbone transport and service termination. The implementation of this architecture follows several steps. Building a common SPB topology, define and configure the same backbone VLANs on all switches on the infrastructures. The BVLANs act as a transport VLAN within the SPB fabric. By mapping different services to different VLANs, the network achieves pre-service load balancing, allowing multiple equal cost paths to be used simultaneously across the fabric. And then specify a control BVLAN identical across all devices, dedicated to SPB IS-IES control traffic. This BVLAN is used by IS-IES to exchange topology and service membership information, including backbone MAC addresses, ensuring that all SPB nodes share a synchronized view of the network and can compute deterministic forwarding paths. And then we enable SPB IS-IES on every node, identify and declare the SPB interfaces or port participating in this backbone. These operate are performed only once during the initial deployment of the infrastructure. The second step, we configure the services, and finally, the SAP. Let's dive to the demo. In this demo, we will use GNS3 to validate our full SPB automation workflow. Our lab is composed of 4 ALE-AOS 8 switches and 2 client pieces connected to port 115 on switch 1 and switch 4. Let's assume these 2 clients represent 2 different sites. So the first step is to verify that all switches are running with no SPB configuration, and we can do this in CLI or directly on Nautobot. In Nautobot, in module devices, for example, for switch 1, in configuration, we can confirm there is no SPB-IES-IES configuration, and the same for all devices. Once confirmed, we move to the SPB environment. SPB configuration in this demo is organized into 3 major steps: SPB topology or backbone, SPB services, and SAP, Service Access Port. But before configuring anything, we need to ensure that AWX will automatically push configuration to the switches. To achieve this, we configure 3 dedicated webhooks here in Nautobot. SPB interface for topology, SPB SAP for Service Access Port, and SPB services for services. And each with a body template that passes dynamic variable to AWX. Each webhooks trigger a specific REST API request pointing to know a job template ID in AWX. And in AWX, we already have a project linked to our Git repository an execution environment containing the ALE-AOS collection, and a job template where we can clearly see the template ID in the URL. Back in Nautobot, under the SPB module, we start with SPB topology. We now configure the topology name, for example, Acme Enterprise, the control BVLAN, and the data BVLAN, which must be identical across all devices. All infrastructure devices the SPB interfaces for each switch are by default on point-to-point, hello interval to 9 seconds, and multiplier to 3, and metric to 10. And priority in interface type point-to-point, it's not needed. Once saved, our SPB backbone is ready, and the webhooks trigger AWX automatically. And from AWX, we see the job starting, receiving all the required parameters from Nautobot and pushing the configuration. From CLI or directly on Nautobot, we can see the change on the switch configuration. For example, on switch 1, you can see all BVLANs are created and control BVLAN and all interfaces and admin state enabled. Now we can move to the step 2. In Nautobot, now configure the SPB service. devices, the service ID, ESID, VLANs, and you can also choose other options. Service is created, and we see the 4 jobs are starting for switch 1, switch 2, switch 3, and switch 4. And all parameters are received. The configuration was pushed. And we can verify this directly on configuration in Nautobot. This time, for example, in device 2, so we can see all BVLANs control and interfaces are created, and now we have the service created too. Now we can move to the final step on SPB in SAP. We choose the service, for example for switch 1, device, interfaces we want, but in our case is 115 where our PC is connected. And here we specify our encapsulation. For example, 0 and 20. Or 20 is just an example in this case. And we will create the same one for the switch 4. Device, interface of this device, and now our SAP for switch 4 is created. In AWX, we can see jobs are starting, and we received information needed. And we can verify that in the configuration of switches. Here now we have our service access ports are enabled. And same for the switch 4. To validate everything, we simply ping between the 2 client PCs connected on switch 1 and switch 4. Our IP in PC2 is 10.10.1.5. Successfully connectivity confirmed that the SPB backbone services and SAP are fully operational. So now your SPB configuration fully automated, deployed, and validated using. The code used for this demo is available on the Spacewalkers Developers Center. This platform brings together all the official ALE API repository modules and tools, plus tons of community-driven contributions. And the best part, contributions are always open, so feel free.
Thank you for your attention. We hope you found this session useful. You can find all the code examples used in this tutorial at spacewalkers.com Developer Center. Take care and see you in next time.